Good afternoon, class.
Good afternoon, Mrs. Kiwat, and I make it to the university.
So welcome to our lesson. Still in the topic structure and bonding. We already looked at ionic bonding, and that is a type of bond where there is total transfer of electrons from one atom to another, and the bond formed hold the atoms together. The atom that loses an electron forms a positively charged ion, while the atoms that gain an electron forms a negatively charged ion. These two negative oppositely charged ions form a mutual force called a bond, and because of that total transfer of gain of an electron, then there is formation of a ionic bond. Now in this kind of bonding, covalent bonding, we shall look at a case where atoms have to contribute a pair or pairs of electrons which are to be shared by both equally. And in this kind of bonding, it is mostly between nonmetals. It is between nonmetals. An example of a nonmetal? An example of a nonmetal. Yes? Louder? Oxygen. She's saying oxygen atom. Yes, oxygen atom is a nonmetal. Good. Another nonmetal? At the back? Another nonmetal, please. Yes. Argon, correct. Any other? No. Aluminium is a metal. So nonmetals are found in the periodic table between group 4. We have carbon in group 4, all elements in group 5, all elements in group 6, all elements in group 7 constitute nonmetals. So if you want to know to get nonmetals, you get from group 4 up to group 7. Now, she talked of oxygen. Oxygen has atomic number of 8, and therefore its electron arrangement is 2, 6. This oxygen atom has 2 energy levels and 6 electrons in the outermost energy level. Taking you back to the previous topic, in ion formation, we are told these ions, atoms, to be stable, have to either gain electrons or lose so as to attain two states. One of the states is duplet state. This is a case where an energy level is complete with 2 electrons. And this applies to only atoms that have 1 energy level. Which atoms are these that are made of only 1 energy level? From the periodic table, yes? Yes, a clap for her. Hydrogen. Hydrogen has 1 energy level, and therefore, for it to be stable, it should attain a duplet state where there are 2 electrons in the outermost energy level. And then we have the other state, which applies to those atoms with more than 1 energy level, which is octet state. A clap for her. Octet state. That is a case where the outer energy level, the second and the other subsequent energy levels become stable with 8 electrons in the outermost energy level. Now, covalent bond is formed between nonmetallic atoms, and during that formation of that bond, then there is contribution of electrons by either similar atoms of a similar element or atoms of different elements. Let's take an example of oxygen. Oxygen, we have said, has electron arrangement of 2, 6. For it to be stable, then it can easily gain 2 electrons to attain a stable state of 2, 8, rather than losing 6 electrons. So it is easier. It uses less energy to acquire 2 electrons to its outermost energy level so as to attain a stable configuration of 2, 8, which we are calling octet state. Now, an oxygen atom oxygen does not exist as atoms. They exist as molecules made of 2 atoms. For example, O2. Here we have 2 atoms of oxygen, which have covalently bonded. This being one of the atoms, the nucleus is there with 8 protons, and the first energy level 2. This is an oxygen atom, the structure of an oxygen atom. It has 2 electrons in the innermost energy level and 6 in the outermost energy level. So for it to be stable, it has to bring in 2 electrons to its structure. And it can only do this by pairing with another atom. And in this case, we shall show only the outermost energy levels. We will show only electrons for both in the outermost energy level. So we have that bonding to that. One atom of oxygen bonding to another atom of oxygen. This first oxygen atom with 2,6 arrangement has 6 electrons. We shall show only 6 electrons, not both the 2 and 6. We will show only for the outermost energy level, which is 1, 2, 3, 4, 5, 6. Now, this other one also have the same electron configuration. This time we shall use dot so that we can easily identify the 2 separate atoms. So we have 1, 2, 3, 4, 5, 6. Now, if you see, each has its own 6 electrons. Each 6 own electrons. And for them to be stable, each require how many electrons? Each requires 2 electrons. So they are going to contribute. This one atom is going to contribute 2 electrons to the sharing region. This is the sharing region for both. Any electron placed here will be shared by both equally. And we have said they contribute electrons equally. So this one requires 2 electrons to be stable. So it will contribute 2 for it to receive 2. For it to receive how many? 2. So finally, we shall have each remaining with less by 2. So that we have 1, 2, 3, 4 for itself, and these 2x to be shared by both. So that when we want to confirm if they are stable, we count all the electrons remaining outside and the electrons in the sharing region. So look at oxygen. The first oxygen atom has 1, 2, 3, 4. Then we add all these 4. All these 4. These dots belong to this oxygen, this X belongs to that one, but once they have come to the sharing region, then they will be shared equally by both. So for this first oxygen atom, we have 1, 2, 3, 4, 5, 6, 7, 8. Is it stable?
Yes.
Yes, now that oxygen is stable. This other one have 1, 2, 3, 4, 5, 6, 7, 8. Is it stable? Yes. Now oxygen molecule exists as a diatomic molecule. Di here means 2, where 2 atoms come together, they contribute equal pair of electrons. These are 2 pairs of electrons. Why am I saying 2 pairs? Because we have an X and a dot making one pair, another X and a dot making the second pair. These are 2 pairs of electrons mutually shared by both atoms. And this is the way covalent bonds are formed in oxygen. So we can shorten this by showing only, we can show the bonds using hyphen. So between this and that, there are 2 covalent bonds. There are 2 covalent bonds, and oxygen is stable. Let us use another example of nitrogen. Nitrogen, to which group does nitrogen belong? Nitrogen belongs to group 5 of the periodic table. So this nitrogen, being number 7, has electron arrangement of 2, 5, of 2, 5, 2, 5. Again, nitrogen does not exist as an atom. It exists as a diatomic molecule where 2 atoms of nitrogen bond through a covalent bond to form nitrogen molecule. So for us to proceed to bonding in nitrogen, we need to know the electron arrangement of nitrogen. Once you have the atomic number, it's easier for you to get the electron arrangement. That is 2, 5. 2 electrons in the first energy level, 5 electrons in the outermost energy level. Now with this arrangement 2, 5, is nitrogen stable? When do we say nitrogen is stable? When do we say nitrogen is stable? Correct. When it has 8 electrons in the outermost energy level. So how many electrons does it miss? Does it lack? How many does it lack? 3. 3 electrons. Now for it to be stable, it needs to gain 3. And nitrogen, we have said, exists as a diatomic molecule with 2 atoms. For this to be formed, then a nitrogen atom is covalently bonded to another nitrogen atom. Each nitrogen has the same electron configuration with the same number of electrons in the outermost energy level. So the easiest way to know the number of electrons required or given out to the sharing region, you look at the outermost energy level. With this 5, then it means it needs 3 more to make to 8, which is the stable electron state. So those 3 are contributed by each. This will contribute 1, 2, 3. Out of how many that are in the outermost energy level? 5. How many will remain for it in the outer energy level? 2. So those 2, we place them here. The first nitrogen has contributed how many electrons? 3, and has remained with 2 on the outer side. Then this other nitrogen have the same electron configuration. And here we are going to use a dot so that we can distinguish. So this nitrogen will contribute 3. 1, 2, 3. How many remains on the outer side? 2. Again, to confirm that each is stable, we count the number of electrons on the outer side and in the sharing region for both. For the first nitrogen, let's count. Here we have 1, 2, 3, 4, 5, 6, 7, 8. Is it stable? Yes, it is now stable. The second one, we have 1, 2, 3, 4, 5, 6, 7, 8. Now we have another molecule which undergoes covalent bond to form a molecule, to form one molecule which will exist as a unit and can react as a unit. Again, covalent bonding is a bond formed when atoms forming the bond contribute electrons equally and to be shared equally by both atoms. They can be atoms of the same element, like in nitrogen and in oxygen, and can also be atoms of different elements. Can be atoms of different elements. For example, ammonia, formation of ammonia molecule. We have nitrogen and hydrogen together, bonding to form a molecule. Nitrogen atom comes from nitrogen element. Hydrogen is from element which is called hydrogen. So these are 2 different elements. We have nitrogen and hydrogen. That is the formula for ammonia, NH3. That means in this molecule there is 1 nitrogen atom and there are 3 hydrogen atoms, and these atoms are bonded to this nitrogen covalently. Covalently here I mean each atom will contribute electrons to be shared, and remember the bottom line is equal number of electrons. Each will give equal number of electrons. There is none that gives more than the other. They will both give equal number. Back here, you saw nitrogen contributing, this nitrogen contributing 1, 2, 3, and the other nitrogen contributed 1, 2, 3, equal number. Same as this case when there are 2 different atoms of different elements. Let us look at bonding in ammonia. We need to know electron arrangement of each atom before we continue. So nitrogen is as atomic number of 7 with electron arrangement of 2, 5. One hydrogen on the other side has electron arrangement of only 1. Being number 1 in the periodic table, then it will have atomic number of 1. How many energy levels are in nitrogen? How many energy levels does nitrogen have? 2. So it has the first energy level with how many electrons? 2. And let me show it inside here. And the second energy level with 5. This is how nitrogen looks like. Sorry, these are more. These are 4, then 5. But in covalent bonding, we don't show all the energy levels. We will only show the outermost energy level. And that means we shall have only one energy level like that. One nitrogen surrounded by 3 hydrogens. So we shall have the 3 hydrogens here, another hydrogen, and another one here to make 3. Remember again, we have said because they are sharing electrons, they will share equal number of electrons. Each hydrogen has only 1, and it requires only one to attain the duplet state. You remember we defined the duplet state as the stable state where there are 2 electrons in the outermost energy level. So this one will require how many electrons to be stable? Only 1. From who? From this atom nitrogen. So one hydrogen will contribute, let's use X for hydrogen and dot for nitrogen. So this will contribute 1X and will be given 1 dot to the sharing region. And then we shall have this hydrogen 1 and a dot. This one X and a dot. X from hydrogen, dot from nitrogen. X from hydrogen, dot from nitrogen. Back here, how many electrons do nitrogen have in the outermost electron? 5. How many has it given out to the 3? 1, 2, 3. How many does it remain with? 2. So we put those 2 here for nitrogen. Those 2 that are remaining. Those 2 that are remaining. Remember to use dots because we were using dots for who? Nitrogen. Now, let's confirm if they are stable. This hydrogen has 1, 2. Is it stable? Yes. Hydrogen, 1, 2, stable. This other hydrogen? 1, 2, stable. Nitrogen, 1, 2, 3, 4, 5, 6, 7, 8. Now they are stable. Each being stable and have formed a bond. There is a force that keeps them together, which is called a covalent bond. So we can still show that alternatively by showing, we can shorten that without using the circles to show the energy levels. We can show the hydrogen here, here, and there. We have this X and a dot, X and a dot, X and a dot, and the 2 dots. The same ones. But this time we have not used the circles, we are only showing the dot and cross. This pattern of showing bonding is called dot and cross, use of dot and cross diagrams to illustrate bonding. Use of dot and cross diagrams to illustrate bonding. You can still shorten that by not showing the dot and cross, but we only show the bonds. So that we have nitrogen surrounded by H, another single covalent bond to an H, another single covalent bond to an H. And then up here, we show the remaining electrons. These electrons that are unpaired, unshared electrons are called lone pair. Lone pair of electrons. Lone pair of electrons. They are still available for bonding. They can still undergo bonding, and we shall look at that when it comes to coordinate bonding. So ammonia is an example of bonding between atoms of different elements. Between atoms of different elements. Any question up to that point? So that is bonding in ammonia. Any other compound that you know that belongs to different, that have different atoms? Different atoms. We have, yes, water molecules, they undergo covalent bonding. Another type of bonding, of molecule that undergo covalent bonding, we have carbon-4 oxide. Carbon-4 oxide. Water is made of hydrogen and oxygen. Here we have one oxygen atom bonded to 2 hydrogen atoms, through the same method of bonding. Covalent bond called coordinate bond. And it's another type of covalent bonding. It involves similar, it undergoes the same sharing of electrons. But the difference between coordinate bonding and covalent bonding is that in coordinate bonding, the electrons to be shared are contributed by only one member. Contributed by only one member of the pair that is forming a bond. For example, carbon 2 oxide. Carbon 2 oxide. Carbon 2 oxide has a chemical formula of CO. You can see there is a carbon and an oxygen atom. Carbon is a nonmetal, oxygen is a nonmetal. Carbon has electron arrangement of 2, 4. Oxygen has electron arrangement of 2, 6. Looking at the two, each require different number of electrons to be stable. They don't require the same. Like carbon requires 4 electrons. Oxygen requires only 2. So carbon requires more than oxygen. And they still have to share. So we will show only 2 circles like that. A carbon and oxygen. And then we have the sharing region here for the electrons to be shared. We consider the number of electrons that each require. Carbon requires 4, oxygen requires 2. Let's begin with equal number first, which will be similar for both. That means 2. So we shall take 2 first from oxygen and 2 from carbon. 2 from carbon. We arrange in that order, beginning with x followed by a dot, x followed by a dot, so that they form a pair. A pair is made of electrons from each atom forming the bond. So we have those ones. How many electrons remain outside? Out here, after removing 2, will remain 4. So we show the 4 out here. We shall use x, 1, 2, 3, 4. Coming to this side, this carbon contributed 2. How many electrons remained?
2.
Subtract, they remain 2. Those 2 electrons, we contribute them here. We distribute here like that. Now let us count if they are stable. Begin with carbon. 1, 2, 3, 4, 5, 6. Is it stable? No. It's not yet stable. Look at oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Oxygen is already stable before carbon is stable. And still, the two have to, they have to pair. So we cannot get electrons elsewhere. Those electrons to be shared still have to come from that region. So what we do is to get more electrons from who? Oxygen. The one with more. The one that has more will contribute some more electrons to the sharing region to be paired with this carbon, and then they will share. So we have this one contributing 2 more electrons. Why 2 and not 1 or 3? Because carbon is still lacking 2. And again, because they have to be an even number so that they make a pair of electrons. So this a pair of electrons from oxygen will be contributed to the middle here for sharing. And you see I've used the same illustration, x, x. This will help us trace that these XX were contributed by who? Oxygen into the sharing region, and you realize carbon has not added anything. Carbon only contributed 2 and has not added any more because it is the one that is in need of the 2 electrons. So let's count again. 1, 2, 3, 4, 5, 6, 7, 8. Is it stable?
Yes.
Yes, it is still stable. Let's look at carbon which was not stable. 1, 2, 3, 4, 5, 6, 7.
8.
Yes. Is carbon stable now?
Yes.
Yes, carbon is stable. So you realize that there are 2 types of bonds here. There is a shared pair of electrons shared pair, meaning there are covalent bonds existing here. And now, where we have the shared pair contributed by one member, which now forms the coordinate bond. So we have a carbon covalently bonded twice to oxygen and a single pair which is coordinate bond formed between the two, carbon and oxygen. That is bonding in carbon 2 oxide. So the similarity here is that there is sharing of electrons. Sharing of electrons. But the difference is the number that is being shared, coming from a different, in covalent, the shared electrons come from both atoms, but in coordinate bonding, the shared pair of electrons are contributed by one member of the pair that is forming the bond. Like there, it was oxygen that contributed more. After contributing the two which were equal to the ones that carbon contributed, it still contributed two more extra from who? From oxygen. And that forms a covalent bond. Now the topic is structure and bonding. So we look at bonding and finally the structures formed after the bond has been formed. After formation of those ionic bonds, then the structure formed is giant ionic structure. In this case now for covalent, we have two types of structures. Elements here, atoms here share electrons, either contributed by both or different, but finally they form a huge structure, which is either molecular or atomic. So we have two types of structures formed by this kind of bonding. The first type of structure is giant molecular structure. Here we have the structure being made of several molecules. And remember, one molecule is covalently bonded. But between a molecule and another molecule, there is a force that keeps them together so that they exist together, called intermolecular forces of attraction. So once their molecules have been attracted, they form one single structure which exists and is called giant molecular structure. Under the same covalent bonding, we have another structure called giant covalent structure. Giant covalent structure. So they are more or less similar because they arise from either coordinate or covalent bonding. But their properties differ in terms of solubility, in terms of melting and boiling points. So for giant molecular structures, most of them exist as gaseous at room temperature, and the reason is because they have low melting and boiling points. What do we mean by melting point? Melting point. What do we mean by melting points? It is the temperature at which a substance changes state from solid to liquid. And that temperature is determined by the strength of the bond. If the bond formed is weak, then the energy required to break those solids to change to gas will also be very low. And if the force formed is strong, then the energy required to break those atoms, those substances in solid state to liquid state will be high. The energy required will be high. So in giant molecular structures, we are saying their melting and boiling points are low. What does that tell us about these structures? That the intermolecular force of attraction is weak. For example, oxygen. Between an oxygen and oxygen atom, it exists. There is a pair of covalent bond. A pair of covalent bond. This pair of covalent bond combine the two and forms oxygen molecule. This oxygen molecule is held to another oxygen molecule by a weak force which we are calling van der Waals force. van der Waals force. From the term there, weak, normally refer to it as weak because it is that van der Waals force is a weak force that holds one molecule to another molecule. But within the molecule, there is a strong force called covalent bond. But when it comes to melting and boiling points, we don't look at covalent bond. We look at the intermolecular force, the force between molecules, and not the force between atoms. I hope you are getting the difference between atom and molecules. Atom here is that particle, smallest particle of the element. So, for example, oxygen, the two atoms covalently bond, then they form a molecule of oxygen which is held to another and several other oxygen molecules by weak van der Waals forces. So when those molecular substances are heated, they quickly change state because the force between them is very weak, very weak. Again, that is the reason why most of them exist as gaseous at room temperature. What is the approximate room temperature? 24, 25 degrees Celsius. And that temperature, as much as you take it as a very low value, it is still high for molecular substances. That's why by the time we have room temperature, most molecular substances have already changed state from solid to liquid and to gas. So you see their boiling points are way below room temperature, way below room temperature. Now, we have some molecular structures having molecular, we have some compounds that have molecular structures, but you find that they still have high melting and boiling points. So, there's something about the melting and boiling points again in relation to molecular masses. The more the molecular mass, the more the relative molecular mass, then the stronger the intermolecular forces of attraction. The more the mass, then the stronger the intermolecular forces of attraction. And this will also affect the melting and boiling points. So that the greater the molecular mass, then the stronger the intermolecular force, and finally the higher the melting and boiling points. But you have some, we have for example water. For example, water and ethanol. We have water having the relative atomic mass, molecular mass of 18, but has a boiling point of a melting point. Yes, you can have the boiling point of 100 degrees Celsius. Then we have ethanol with a mass of 46, but boils at 78 degrees Celsius. So you realize that this one with lower melting point will have a low melting point. And the difference is because of there is an additional bond in water called hydrogen bond. Water have an additional bond called hydrogen bond, which make molecular structures to be stronger. Molecular substances to have a strong force and therefore a higher melting and boiling points. But molecular substances that lack hydrogen bond, that do not have hydrogen bond, will always have low melting and boiling points. Those that have a hydrogen bond in them will have a higher melting and boiling point because hydrogen bond is stronger. So when you compare hydrogen bond and intermolecular force called van der Waals forces, hydrogen bonds are stronger than van der Waals forces. They are stronger than van der Waals forces. And lastly, conductivity. Molecular substances do not conduct electricity. Molecular substances, they do not conduct both heat and electricity. The reason? They lack delocalized electrons or mobile ions. Substances responsible for conductivity are mobile electrons and mobile ions. But molecular substances lack mobile electrons, they also lack mobile ions. And the reason is because before forming the structure, they had bonded in pairs, so they used their electrons in bonding and therefore do not have any free electron. So they do not conduct heat and electricity. Again, these are the properties. Most are gaseous at room temperature, some are liquid at room temperature. Another property we have said their melting and boiling points are low. Melting and boiling points are low, except for those that have a hydrogen bond. Except for those that have an additional hydrogen bond. Otherwise, most of them have low melting and boiling points. And finally, we have said they do not conduct heat and electricity simply because they lack delocalized electrons, they lack mobile ions. And one last one, the fourth one, is that they are insoluble in water. They are insoluble in water because they are non-polar. But you'll still find a few of them showing a disparity. They are molecular, for example, ethanol, but still dissolve in water. What causes that? It is because those that dissolve in water still have the additional hydrogen bond. So any molecular substance with a hydrogen bond will be able to dissolve in water because hydrogen makes it polar. Yes, unless you have a question.